Take a look at this processor. Every second, a modern CPU is bombarded with thousands of simultaneous, competing demands. Some demands come from you. When you move a mouse, you expect an immediate, millisecond response. Other demands operate entirely out of sight. Massive system updates don't require your instant attention. Pushing all of these vastly different tasks into one single line creates a massive traffic jam. Notice what happens in this funnel. When a slow-moving background process enters the queue first, it takes up all the processing space. Your lightning-fast keystroke is completely stuck. In reality, this is why your entire computer feels laggy and unresponsive. To prevent this gridlock, OS engineers abandoned the single-line approach entirely and adopted multi-queue architecture. The simplest method is multi-level queue scheduling, or MLQ. It relies on strict, rigid sorting. A more complex approach is the Multilevel Feedback Queue, or MLFQ, which adapts continuously. The way these queues are structured determines if a system keeps moving or grinds to a halt during spikes. Let's look at exactly how both of them handle the load. This diagram shows the core mechanic of MLQ. Processes are permanently assigned to specific fixed categories. Because the queues are separated, the operating system can tailor exactly how each line runs. The interactive queue might use round-robin scheduling for fairness, while the background queue uses a first-come, first-serve approach. But there is one strict rule. The CPU will only look at a lower-level queue if the ones above it are absolutely 100% empty. This design is incredibly predictable. The operating system knows exactly where every task belongs, requiring almost zero management overhead to keep things running. However, this same predictability introduces a specific trade-off. We call this starvation. If high-priority tasks keep pouring into the top queues, the CPU will never, ever grant processing time to the bottom queues. If a fast task gets miscategorized and dropped into that bottom queue by mistake, it is trapped. It will sit there indefinitely while the top queues hog the processor. Locking tasks into permanent tiers is too dangerous for unpredictable user inputs. Engineers need an alternative that can adjust on the fly. By strictly locking task priority, MLQ guarantees critical operations run instantly, even if it means abandoning background tasks entirely. To solve that starvation problem, engineers developed the Multilevel Feedback Queue. Look at this three-tier system. The foundational difference here is that processes are not locked in. They can move dynamically between the queues based on how they behave. Every new task starts at the very top, but if a task eats up its entire allotted time slice without finishing, the system demotes it downward. Because of this demotion, heavy, CPU-bound tasks automatically filter down to the bottom tier. This keeps the top tier completely clear for your fast, interactive clicks and keystrokes. But pushing heavy tasks to the bottom still risks starvation. To fix that, MLFQ introduces a mechanic called aging. Watch this timer graphic. If a task waits too long in a bottom priority queue, the system intervenes and automatically promotes it back to the top. Aging guarantees that every single process, no matter how dense or low priority, will eventually receive execution time. The OS actively learns task behavior on the fly. It doesn't need to know what a process is beforehand. It just watches how it acts and sorts it accordingly. But there is a heavy trade-off. This dynamic movement requires high architectural complexity. The CPU actually has to spend its own valuable processing cycles constantly monitoring wait times, adjusting its timers, and executing queue movements. That is computing power being spent on traffic control instead of actually finishing tasks. MLFQ prevents starvation and keeps the interface perfectly responsive, but it demands a permanent tax on CPU efficiency to manage its own rules. This matrix gives us a direct look at the hidden costs and benefits of both algorithms side by side. On queue movement, MLFQ is strictly fixed in place. MLFQ is highly dynamic. For starvation risk, MLFQ carries a critical vulnerability. Thanks to the aging mechanic, MLFQ drops that risk to near zero. Looking at system overhead, MLFQ leaves a lightweight, low-impact footprint. MLFQ requires a constant, heavy monitoring tax. Finally, tuning complexity. MLFQ is a simple setup out of the box, whereas engineers must perfectly balance the time limits in MLFQ to prevent system instability. One algorithm relies on rigid simplicity to succeed, while the other relies on constant micromanagement. Theory only gets you so far. If you are a system architect, you have to decide which one to actually implement. This flowchart breaks down your decision to one crucial question. Are your workload categories highly predictable? If the answer is yes, meaning you are building specialized embedded systems, dedicated batch processors, or single-purpose servers, choose MLQ. You will guarantee rock-solid predictability and waste the absolute minimum amount of CPU power on management. If the answer is no, meaning you are building general-purpose desktop operating systems, cloud environments, or smartphones where user behavior is completely chaotic, choose MLFQ. Paying the overhead tax is completely worth it if it adapts to the user and prevents their interface from freezing. Ultimately, the goal isn't to find a universally perfect algorithm, but to match the CPU's logic to the environment it's designed to handle.